This is problem number 4958. In this problem, I'm going to explain what the Lagrange's identity is and how to prove that. For this particular scenario, I'm going to consider only two-dimensional case because n-dimensional case is a little bit tricky, and I'm going to get to this in my next episode. But here, I would like to focus entirely on two-dimensional case. So for a two-dimensional case, Lagrange's identity looks like this. Suppose we have vector u, which looks like a and b, and vector v, which looks like c and d. These are two components of these vectors. Now, by Lagrange's identity, it is given that ad minus bc square equals to the second norm of this vector product, second norm of the vector v square. Second norm is the magnitude of this vector, essentially. This is the same thing. Difference with u, v scalar product, square. So how to prove that? In order to prove that, we just need to resolve the right side of the equation. That's basically it. So in order to resolve that, we have to assign, well, basically we have to find out that second norm square of the second norm of vector v, vector u, and vector v, it is essentially the sum of squares of their coordinates, which is a and b, and the second norm for square of the second norm for v, it is essentially c square plus d square. And if we try to find their product, that would be a square c square plus a square d square plus b square c square plus b square d square. And now if we want to find the scalar square of the scalar product, this is a c plus b d square. And now if we try to find the difference between them, that would be a square v square minus u v square. That would be like, well, these two will cancel each other, and then from this step it follows that a square d square plus b square d square minus 2ac bd. We can actually use the commutative property here, associative and commutative properties of the scalars, and we're gonna get that is essentially the same as ad minus bd. We basically completed the square here. Well, yeah, that's the proof behind the Lagrange's identity for a two-dimensional case. So one of the reasonable questions that you might ask, that you might have, how can we potentially apply this Lagrange's identity in practical sense? Well, there's a good problem for this to demonstrate that. Now, let's imagine we have the parallelogram A, B, C, and D. Here it is. This is the parallelogram. And this parallelogram is defined in three-dimensional space. And the problem asks us to prove that the square of this area of this parallelogram, it is essentially the sum of projections of the area onto corresponding planes. That's sxy, the projection for xy plane, oxy plane, plus square of yz plus sxz square. Now, we already know that S is essentially AB times AD times sine the angle between them. So, I mean, that's a well-known fact from planimetry, from Euclidean geometry. Let me denote this side as the vector A and this side as the vector B. And this will turn into the following identity, AB times the sine of their degree, which is the absolute value or magnitude of the vector A and B of the cross product of their vectors. We know that cross product of these vectors is the determinant of third order I, J, and R with the following components A2, A3, A3, B1, B2, B3, where these are components or coordinates of the vectors A and B accordingly. So what is required here is to express these x and y, x, y, z, and how they look like on x as xz. So by definition, x and y, it is the magnitude of projection of vector A onto plane xy times the same for B and degree between them, which is phi, where x and y projection is like a1, a2, but we're gonna drop the third coordinate, we're gonna drop it. So we're kind of imagining that like as they were placed on the same plane where z equals 0. So that would be their projection. And the same for bxy, that would be b1, b2. If we take a look at the following determinant, let me see, a1, a2, and b1, b2, then this determinant would be equal a1, b2 minus a2, b1. But what is that? It is exactly our Lagrange's identity, which is, if we try to find the square, right, the square of this determinant would be by Lagrange's identity bc, right, a, b, c, d, yes, exactly. So that would be equal to vector A, vector B, their magnitudes, the square, minus a and b, the square of their scalar product. Now, this is a square, b square, minus a square, b square, and by the formula, This is cosine square phi, which is the same as a square b square factored out, 1 minus cosine square phi, which is by trigonometrical identity gives us a square b square times sine square phi. Consequently, if we take square root here, this is going to give us the absolute value of determinant equals to a1 magnitude, b magnitude, sine phi, given phi lies in the following interval from 0 until p2 included, because sine should be positive. That all looks good. And what is a and b here? Well, a and b here is exactly our projections because they are given by only two coordinates. We're kind of dropped the third component here. So we can conclude that xy is essentially the determinant of a1, a2, b1, b2. And actually the same rule applies for x, s, y, z. That would be something like with dropped a1, a2, a3, b2, b3 here, the absolute value of that. And we can do the same for x, z, which would be equal to, in an analogous way, a1, a3, b1, b3. And so, what is the cross product? The cross product is I, a2, a3, b2, b3, minus j, a1, b1, a3, b3, plus r, a1, a2, b1, b2. And therefore, the magnitude of this cross product is kind of the sum of these squares, and these squares, these minors, are exactly our projections of our area into corresponding planes. So from that follows that our s square equals to xy square plus s yz square plus xz square. So this is the practical definition of our Lagrange's identity on two-dimensional space and how we can potentially apply that in practice.